Good morning. It is fantastic to have you here this fine Tuesday morning. I am just truly delighted to welcome Michael Walsh as our next speaker. My name is Vladimir Bulovic. I'm the director of MIT.nano. I have a privilege of hosting these Nano Exploration seminars. Michael today will tell us about Solidstate platform for a Boston quantum network. His work has recently culminated in a PhD from Dirk Engeland's group, and he's heading to California to continue his quantum explorations. Indeed, the world of quantum networks is upon us, and Michael will tell us exactly how close it is. So Michael, in a moment, I'll let you take over. Those of you who are tuning in, I see most of you have already turned off your video and muted your feed, and that is great. That speeds up the bandwidth of the rest of us. That being said, if you have any questions, please hold them till the end of the talk. At that point, you can raise your hand and ask a question, or alternatively, send a chat, and I will relate your question to Michael. Michael, please take over.
Thank you, Vladimir. Hi, everybody. So my name is Michael, and today I'll be talking to you about some of the work that I did during my graduate PhD in an effort towards building a solid-state platform for a Boston quantum network. So the goal here is to be able to use this for quantum information, such as repeaters for networks, nodes for a cluster state quantum computing. And for that to be possible, we are going to want identical photons from different nodes, as well as we're going to need identical photons from the same node over time. And so this means we're going to need a high optical coherence for our quantum sources. And we'll be able to measure that by a stable narrow optical line width, but we'll get into the details later. So there's really three things that I want you guys to be able to take away from this talk. And it's how do we incorporate these qubits into the device in the first place? What are the consequences of using this process? And how can we begin to think about scaling this to a device level system that could actually be used in a larger network? And so actually this is already underway. We have a set of fibers, optical fibers that connect MIT Lincoln Laboratory, MIT, and Harvard that build up this local Boston quantum network. And at each of these nodes in the network are housed a set of quantum memories. And these quantum memories can emit a photon into this network such that if Lincoln Lab emits one and it travels to MIT, MIT can then receive it at its node and subsequently then emit its own photon to Harvard. And the idea is that through this process, we're able to build up entanglement across all of these nodes. And entanglement is a valuable resource for quantum key distribution, distributed quantum computing, blind quantum computing, clock synchronization, or more generally just metrology. And so for the rest of this talk, I'm going to focus on a diamond implementation of this quantum node. And so I'll start by discussing some of the qubit platforms, the entanglement protocol, and then jump into some of the device physics, and then spend the last half talking about the workflow and analysis that goes into the building such a complicated device. All right, so qubits come in all different shapes and sizes. Superconductors, you've probably heard of on the news recently if you're plugged into this kind of thing, but it seems to be one of the more common choices for industry. This is an example of D-Wave's Orion chip, where that little black square in the middle may look something like this, which happens to be an IBM chip, but it's a 4-qubit chip, again, superconducting. One of their smaller ones, they recently really scaled up the number of qubits. It can be trapped ions, trapped by an electromagnetic field, and then interfaced with lasers or an optical field to read and write to the quantum memory. It can be light itself. China demonstrated they launched a satellite that was able to connect 2 different ground nodes through an optical free space link and distribute entanglement across a small network that way. It could be electrons, which is pioneered by Microsoft, quantum dots from Princeton and HRL, and solid state defects, which is what we're going to focus on today. And specifically, these solid state defects are optically active. So we're going to be able to take advantage of the fact that we have photons as well as an atomic-like memory. And the challenge will be to make these communicate with each other via entanglement, and to make sure that they're able to store the quantum information that we write to them, i.e. have a long quantum coherence. And so we've seen the advantage of solid state systems because we can map it to the semiconductor industry. This is a picture of ENIAC back in 1945, which took up an entire room, and since then has been miniaturized to a tiny chip with orders of magnitude more power. Similarly, here's a lab in Bristol that is the optical setup for controlling just a handful of qubits. And we're hoping to take advantage of some of the mature tools and processing already developed for other solid state platforms and be able to miniaturize our quantum systems. So qubits and diamond in particular, some of the ingredients that we need for a chip like this is high confinement, such that we can direct the light and route it to where we need it to go. And diamond has a large band gap, so it's transparent to the entire visible spectrum, which is where most of these, the photons live. And it has a high index, which is going to facilitate that confinement. We're also going to need low quantum noise, such that we can retain our quantum coherence or our memory. And diamond can be grown isotopically pure, up to 99.99% of natural carbon-12 isotopes. And carbon-12 isotopes have no nuclear spin, which means we automatically get, for free, a spin-free environment, which means that there's nothing that's going to decohere our quantum memory, at least from that perspective. And a nitrogen vacancy is the defect of choice for a diamond at the moment. It is just a nitrogen atom that substitutes one of the carbons and neighbors a vacancy in the lattice. And given this kind of geometry, we can take a look at the electronic structure that it generates. And we get a spin triplet ground state where the ms equals 0 spin and the ±1 spin are separated by a spin-spin interaction. And we can turn this into a qubit by breaking the degeneracy of that plus-minus state with a magnetic field, and then arbitrarily choose two of these states to be our qubits, and we'll label one of them down and one of them up. We can use a microwave field to address between these two states and perform logic operations. And we can take advantage of another spin-0 excited state and address that using a red laser to facilitate readout of the spin system, as well as to facilitate entanglement. So if we look at the qubit a little bit closer, we can start to compare it to a classical bit, which you might be more familiar with as 0 or 1s, the thing that all computers operate on. But at the end of the day, a 0 or 1 is just a label. So let's go ahead and relabel it down and up, similar to our quantum system. And the thing about a classical bit is that you can have spin down or up, not both. Whereas quantum mechanically, we get a little bit more freedom here. Instead of having one or the other, we can have any superposition of them, which we can represent on the circumference of a circle. Where on the right there, you have a nice superposition between spin down and spin up. But it gets a little bit more complicated than that. A quantum bit has yet another degree of freedom, which is the phase. And that phase we can represent in the third dimension of this circle by extending it to a sphere. And thus we come up with our block sphere, which represents any possible value of a qubit. And so again, we can dress this qubit with a microwave field. And just really quickly, I'm going to show you two different ways we can navigate around this block sphere. And one is called a Rabi sequence, where we just turn on that microwave field and watch what happens with the state. And it simply just progresses around the circumference, switching between up and down and going through superpositions. And then the other sequence is a Ramsey sequence, which we can take information we learned from our Rabi sequence. So first we'll reset the spin, and now we'll just drive it about 90 degrees such that we're sitting on the equator. And at that point, we turn off the microwave field. And when the microwave field is off, this is going to start to precess around the equator in free evolution. And then we can just complete it by rotating it back up to either the spin down or spin up to finish the readout of the state. So to start to consider now multiple qubits and how we can entangle them and have them communicate with each other, we can look at this picture here. So we're going to do this through a photon spin entanglement scheme. And so now we have two qubits, A and B, and we're going to start by initializing them into an equal superposition, as we saw on the previous slide. And then we can address that excited state transition, that optical transition, with a resonant red pulse of light. And so if the qubit is in that spin up state, it's going to be able to absorb this light, whereas if it's not, it won't absorb it. But of course, quantum mechanically, it's in both states at the same time. And so we can write this down. So at that point, spontaneous emission is going to occur just from any kind of atomic system. and it's going to either emit that photon if it absorbed it or not. And so this is what dictates that local entanglement between the photon and spin. And we can write this mathematically by just writing a numeral 1 next to any of the signs that have a up arrow and a 0 indicating no photon for anything that has a down arrow. And we can just simply multiply this state out and separate out the spin component and the photonic component. And then the last step is to let this photon propagate through the network into a beam splitter and thus get detected at one of our detectors. And so the thing that we're going to be looking for on these detectors, between these two detectors, is a single click, a single event of detection. So we can immediately cross out any states that have 2 clicks or no clicks, which leaves us with the click from either one of the top detector or the bottom detector. And we can just easily match up those terms from our measurement and get our resulting spin portion of this quantum state as a balanced superposition between A and B. However, for this to work, these photons must be identical. It must be that when they pass through the beam splitter here, that this beam splitter completely erases the information as to where this photon came from, be it A or B. And so ways that we need to be careful of keeping this indistinguishable is the wavelength, or the color of the photon has to be identical to each other, the line width, and the polarization. And so we can actually, given some of this new information, we can extend our model of the system, which originally just had these single lines representing each state, and actually give it a line width, which is going to be very important for our entanglement fidelity, because as the distinguishability decreases, or we want the distinguishability to decrease such that we have high entanglement fidelity. And so now we want to put this into a device system or a scheme. And so we're trying to build something for a quantum network so we can distribute entanglement among any 2 nodes in the system. And so we can take our 2 nodes, just as we saw before, and our detectors, make a copy of that, and then merge these 2 together. And with this kind of scheme, each of these 4 nodes now has all-to-all connectivity. They can talk to any other node in the network, and we can keep playing this game and extend the network to be larger and larger. And to see this in more of a practical scheme, we can imagine an architecture like this, where your atomic memory interfaces with a switch, connecting it to any of the nearest neighbors, which then has the beam splitter and detection. So now to dive more specifically into our goal here is we're trying to get high yield fabrication of these nanophotonic devices. And specifically getting a 50 nanometer positioning of that quantum emitter in that quantum device. And so we're going to show you how to position structures around the emitters while retaining emitter quality. And so these nanophotonic structures at the end of the day are cavities. And if we were to look at what the light would do without a cavity, given this quantum emitter, it's going to want to just propagate away from itself, but it will stay in the diamond because of the high index. And what the cavity does is it restricts the light from propagating and confines it to the center of the cavity. And if you're unfamiliar with cavities, imagine just putting 2 mirrors facing each other. And these devices, obviously we're not quite using mirrors, but we're using these periodic holes fabricated into the diamond, which at the end of the day is a distributed Bragg reflector, a DBR, if you're familiar with it. But we can verify that this does confine the light using simulation tools. And to see what this effect has on the emitter itself, here's what the NV spectrum looks like without a cavity, which we can map this very closely to our energy diagram that maybe we're a little bit more familiar with. And we see that there's actually a lot of light detuned to the red shifted from our transition. And we can start to reason why this might be. First, we can renormalize our energy diagram here, because the excited state's actually much higher energy than this ground state. So we can go ahead and ignore the other levels of the ground state. And we see that there's actually, there we go. Because we're in a diamond, we're in something that has atoms all around us that are all vibrating around. There's an opportunity for that photon to, instead of decaying straight to the ground state, it could interact with one of these phonons, or the vibration in the lattice. And so if we put a cavity around it, a cavity that's tuned specifically to the transition that we want, we're able to increase the amount of light that comes out of that particular transition. And before we have a cavity, we're only looking at about 3% of the light, the total amount of light that comes out of these NV centers that are in the usable part, that are in that what we call a zero phonon line. Whereas we've demonstrated with a cavity, we can push that up towards 56%. Okay, so for the rest of this, I'm going to focus now on building the process of building these devices and taking steps through to make sure that we're able to build such a complex device. And so we're going to start by looking at the qubit production in a little bit more detail. And then we're going to go through how once we have the qubits in place, how we pick out the ones that we want to actually begin pursuing and engineering systems on top of. And we'll briefly go through what the diamond patterning looks like. But again, we're targeting the pre-selected qubits and patterning our quantum structures on top of them. And then the final piece is going back in and looking at, now that we have our structures on top of our qubits, we have to go in and find the ones that actually worked and the ones that are the best of the best. And with those ones, we can transfer them off of our diamond chip onto this backbone chip that's going to be our device at the end of the day. All right, so we'll start with the qubit production. And just take a quick look at the devices in our diamond again. And again, we have these 200 nanometer thick cavities. And for our quantum emitter to interact with this cavity to the best of its ability, we're going to need to target about the middle of these beams. And one way of doing that is through ion implantation, where we can get a nice tight distribution of our nitrogen ions at a depth of our choosing. And so to look at that in a little bit more detail, we can look at a cross section of our diamond, where the top surface here is the top of the diamond, and we look about 150 nanometers deep. And you'll see in our diamond, we have some amount of native nitrogen-14. And so we're going to implant nitrogen-15 as a way to distinguish between them, which we'll get into in the next slide. But when this nitrogen hits the surface, it's accelerated to about 185 kiloelectron volts. So it's going to crash into the diamond and keep propagating through, knocking out carbon atoms as it goes, leaving behind a trail of vacancies, which are denoted by those purple dots. And we can use some simulation tools to figure out the distribution of those implanted nitrogen-15s, as well as the vacancies. And we see that they line up at the depth that we're interested in. So the next step is to anneal these at 1200 degrees Celsius, such that those vacancies become mobile in the lattice. And they're going to start to perform a random walk until they encounter a nitrogen atom, be it a naturally nitrogen-14 or our implanted nitrogen-15, at which point they'll bind and form what we're after, the nitrogen vacancy center. But importantly, the nitrogen-15s here are going to be at the depth that we need for our devices. So if we look at that level structure again, the next thing we need to note is the nitrogen-14 is a spin 1 nucleus, which gives us 3 hyperfine transitions in the ground state, whereas the N15, our implanted nitrogen, is a spin 1/2 nucleus, which gives us 2 hyperfine transitions. And so again, with our microwave field, we can address these and basically use this as a tag to look at the ones that were implanted versus the ones that were naturally occurring in the first place. And again, we have our resonant laser to address our excited state, which is the thing that dictates our entanglement. So the most important fact that we're going to be looking at here. And it's important to note that this actually splits out into an EX and EY transition, which given transverse strain will split out further, and given axial strain will just shift the energy of that excited state transition. So if we look at this on a confocal scan taken at 4 Kelvin, we can see all of the bright spots in here correspond to fluorescence from our nitrogen vacancy centers. And by sweeping that magnetic field over one of these spots, we can see 3 dips, which in this case represent the 3 hyperfine transitions of the NVs formed from the natural nitrogen. And we can do the same thing with the excited state and sweep our resonant laser over it and see our 2 EX and EY transitions, or known as PLE. And we do this for all of the sites in our field of view, as well as all of the ones that were exhibiting the 2 hyperfine transitions corresponding to the ones that we're more interested in, the implanted nitrogen. But we also keep track of some that we just weren't able to distinguish if it was 2 dips or 3 dips, so we're unclear what the isotope is in the NV. And we can do a sanity check and just make sure that this was caused from our implantation and annealing by looking deeper into the diamond and seeing way fewer NV centers. And so the thing that jumps out here is that the NVs formed from our implanted nitrogen have about an order of magnitude worse line width or broader line width. And we can also see that the splitting between them is also quite a bit larger. So our job at this point is to try and quantify this a little bit better so we can understand what's happening. And so if we look at this for all of the various line widths, for all of the NVs that we see, we can plot it in a cumulative distribution, or if you prefer looking at a histogram. And we see quite easily 2 distinct populations of line widths. And we do note that while there are these nitrogen 15s that exhibit narrow lines, the vast majority of them are an order of magnitude broader than are naturally occurring in 14-based NVs. And if we look at our little cartoon of the implantation process, we can kind of see why pretty quickly. All of the NVs that are implanted or formed from the implanted nitrogen have a much higher likelihood of being surrounded by these vacancies or damage in the defect. Whereas these native nitrogen 14s could be much farther away from that trail of vacancies and have a much cleaner environment. And because we have a built-in strain sensor in our NV, we can actually confirm this from measuring our transverse strain, which if you remember is the splitting, and our axial strain, which if you remember is the position of the transition. And so if we look at both of these together, they both show the same thing. They both show that these implanted nitrogen 15-based NVs are generally exhibiting more transverse strain and a higher degree of variability in their axial strain component, which suggests that the damage from the implantation process itself makes the optical transition much worse and to some point hard to use. Because, so that the higher strain environments, broader optical transitions, and the downside is that this decreases the entanglement fidelity, which spawns new investigations. So we need to look for alternatives to ion implantation, something that produces much less damage to the diamond lattice, or improved annealing techniques and find a better way to heal the damage from the lattice when we anneal the diamond. However, we can still use these NVs without devices to characterize more steps in the process, which is what we'll do. And to that end, we're going to need to scale this process up. So we've seen one field of view on one small piece of this diamond, but we need to replicate this and do this measurement across the entire surface of the diamond. And to do that, we're going to start with so these diamonds are 3 to 5 millimeters in size. So we're going to pattern a QR code coordinate system on that, which if we zoom in, you can see our 2-dimensional codes, which represent a similar thing to QR codes. But we encode the location of that code in the bits of the 2-dimensional code. And so if we look at what our microscope sees, which is about the field of view of 4 of these codes, right here we're seeing the fluorescence from the surface. So each of those bright spots circled by a orange circle is fluorescence from one of these quantum defect centers. And we can grab the position of it in this frame and using machine vision, correlate that to these QR code-like markers, or these location markers, to translate that position in the frame to a position on our diamond chip. And we do this for every possible spot on the diamond. And to see this in action, we can actually look at a time lapse of our microscope walking along one of these 5-millimeter diamond chips, where each of these little green dots on the left corresponds to one of these images on the right. And if we kind of just let this loose, it's going to start to navigate and explore this diamond until it finds as many emitters as it can. And so this process might take about a day or so to complete an entire diamond, but gives us about up to even 500,000 defect centers that are located relative to our global coordinates on this diamond. And we can see just how accurate it is by repeating this measurement, by moving the diamond physically in space under the microscope. And we can see that we actually get about 20 to 30 nanometers accuracy in getting the location of these on our global coordinate system, which is more than enough to be able to pattern our quantum devices on top of them. All right, so this autonomous microscopy enables us to register tens of thousands to hundreds of thousands with the sub 50 nanometer accuracy, again, important for our patterning of devices. And it also allows us to explore different types of registers, which we won't have time to get to in this talk, but worth mentioning. And we've also seen how important statistics are, as we looked at in our qubit production step, and how that was informative and vitally important for moving forward and kind of fabricating these types of devices. So now we're able to, now that we have these NVs in the diamond and we found them already, instead of comparing two different ensembles like we did in the qubit production, we can actually compare the same emitters through the fabrication process. Which is going to pave the way to higher fidelity fabrication of these aligned systems, and importantly, enable process control. And so we can examine what that looks like in our diamond patterning step. I know I mentioned that we don't actually pattern on top of the NVs in this, but there's a lot of other steps that go into this diamond patterning. And so now that we have NVs, we can at least track them through some of those steps. And some of those are like a triacid clean, a 450 oxygen bake, another triacid clean, a piranha clean, an etching structure, and then the 1200 anneal. Bottom line is there's lots of steps that go into patterning our diamonds. And so we can look at these in a little bit more detail and try and track our emitters through each step. So the triacid step is able to remove graphite from the surface. The 450 oxygen bake can remove dangling bonds from the surface, and the piranha clean is a chemical clean, all of which go into making a more pristine environment for our quantum emitters. And so again, if we're looking at this PLE measurement, which again is sweeping our resonant laser across the excited state, we can look at that before and after a triacid clean. And again, the thing that we're interested in here is the width of that transition. So if we go ahead and label width pre, width post, the thing we're interested in is the change in that width. So now we can look at the change in that width for all of the emitters that we have in our tracking system. And if we plot that in the histogram, we actually see a marginal improvement due to just the triacid clean, where we have about a 10 megahertz narrowing or improvement of that optical transition. Unfortunately, this is about as far as we got before things started to shut down, but we actually have quite a bit more data even with just this step. We have the position of that emission, the frequency of it, and we have the splitting of it. So if we plot the frequency of it on the x-axis and the splitting, the splitting on the y-axis, we can plot that in 2 dimensions. And here we're just looking at a control, so nothing happened between the 2 measurements, but you can see it does kind of wander in both dimensions a little bit. But the more interesting thing is to look at what happens after we do our triacid clean. And yeah, we see a little bit more wandering. But the real power of this only comes into play when we start looking at a large number of these things, where we start to see some very interesting features pop out that we had no idea would have existed without looking at these numbers and correlated statistics. So the next step here is obviously to figure out exactly what's going on and why we see the behavior that we do. But I'll have to leave that again for another time. And so we see that the tracking of these registered emitters, so comparing the same emitter before and after each processing step, enables us to build up these correlated statistics, which gives us a better understanding of what's happening and allows us to iterate designs and process steps. So to wrap up here, I want to just briefly touch on the last step of this process, where we go back and look for the nodes that worked and take them off the chip and put them on our final device. And so again, without going too deep into the details, we actually used a different type of emitter here that works better for implantation. But that doesn't matter for the end goal. So for this integration step, we now have something that's patterned all in diamond. So what you're looking at here is a diamond chip, each of these little cells has 8 of those nanowires in them. And so what we want to do is come in with a tungsten probe and pick out one of those nodes, or what we call these quantum microchiplets. And we want to move that microchiplet onto a backbone chip, or the main device, which has electrical control, as well as a photonic integrated circuit layer to extract photons. And so we place that on there, and we're able then to control our NVs or our other quantum emitters electronically, and be able to collect the emission from the quantum emitters. I think the largest device that we have right now has 128 nodes in it. But again, not quite fully quantum yet, but getting there. And so just to recap, we've seen that these engineered NVs exhibit some problematic optical transitions, but has given us new directions to explore, including novel emitters, not NVs, but some other defect centers. And we've seen that this automated registration of tens of thousands of NVs with sub 50 nanometer accuracy is going to lead to higher fidelity fabrication at chip scales. Again, we didn't quite get into some of the novel qubit nodes, but that is a possibility with this microscope as well. And then finally, we've seen how we integrate this with the rest of the technology, with in this case, a silicon nitride or a CMOS backbone, to really facilitate some high-level control of these larger systems. And so all of this comes together to help us with statistical metrology, as well as this chip scale device alignment and process control, all coming together to facilitate our Boston quantum network. And from here, I just want to give a special thanks to the numerous people that helped with this project, from my old quantum photonics group led by Dirk, as well as some collaboration with Delft University, specifically Ronald Hansen's group. And with that, I just want to thank you for your time and open it up for questions.
Thank you, Michael. That was awesome. I have clearly a number of questions to ask you, but rather than me starting it off, I just want to let the other attendees remind you that you can send your questions via chat, or you can raise your hand and I'll make sure I call upon you. Michael, you clearly have had a very broad experience in exploring how to make the idea of a single qubit into a whole network of qubits. And the solid state integration clearly is very much the key to that. I love the fact that you focused on, well, some of these qubits do naturally occur, but not necessarily where you want them. So then the question is, how do you actually qualify how to get them where you want them, or at least identify which ones are in the right place? You mentioned that you didn't have time, though, to tell us about some of the more exotic, new, novel nodes. Would you mind commenting maybe on some of those?
Sure, yeah. So actually, I snuck into the presentation one of those novel nodes. The picture you're looking at here actually isn't NVs. This is one of our more novel color centers, which instead of a nitrogen substitutional, it's a silicon. So this in itself already is something that is a little bit more robust to the varying damage from the implantation process, which at the end of the day was what was able to allow us to fabricate on top of it. But just another quick fact about these is that you'll see that it actually lines up in a pretty nice grid, which is something that is super nice about a silicon vacancy center, which we don't have the luxury of with a nitrogen vacancy center. Because nitrogen, apparently, I'm not an expert on this, but doesn't have a focused ion beam source, whereas silicon and some of these other heavier elements do. So that is one example that I snuck in there. The ones that I didn't sneak in there are more of this trying to combine multiple color centers into one node. And so the idea here is that if we make the node itself a little bit more complicated, we can start to implement even like an error correction on top of a single node, such that we can make that node much more likely of retaining our quantum information for longer. And so let me just see if I have a backup slide here. Actually, so right here is exactly what I'm talking about. So in this particular node, we programmed the microscope to, instead of just go find all of the sites there are, specifically look for a certain type of site where there's multiple emitters. And so the way that the microscope was able to tell that is by looking at this PLE measurement, again, that excited state transition. Oh man, the slide is perfect for this explanation, where we have 3 different emitters here without getting into too much detail. And then using those 3 emitters, in theory, you could start, well, 3 is probably not enough, but you need a little bit more. But you could start to build up this really local set of qubits into a more logical qubit in your network that is error corrected, potentially. There's a lot of steps between getting from multiple nodes in a diffraction limited spot to an error corrected node, but maybe that's for another time too.
Now, since you do have a multiple qubits in your sample, the way you would select the one you want would be by choosing the color. Is that it?
Precisely, yeah. So actually, that's perfect leeway into this.
I haven't seen these slides before, so yes, please go ahead.
Yeah, so here we have those 3 different qubits, A, B, and C, and you can see on the PLE plot there, they're labeled in conjunction with optical transition that is very distinct from each other and separated actually by many, many gigahertz, so many, many line widths. And so what you see up here is just blasting this with green light. And remember, if you remember, the actual light of the transition is red. But again, because this is in a solid state system, we can off-resonantly excite. But if we do it with green, we excite all of them at once. So instead, these 3 slices are exciting it resonantly with the appropriate red light for each of the emitters. And from that, we can actually, assuming that we can fit to our point spread function, which we did, we can figure out where these are within the diffraction limit. And so you're exactly right. You take the way you address them is resonantly rather than off resonantly. And by doing so, not only can you see exactly where they are without interference from another one, you can actually read out their state without interfering any of their neighbors, which is something that's going to be insanely important for an error corrected register, because if you read all of them out at once, or if you destroy all the quantum information at once, well, then you've also destroyed your chance at error correction. Whereas if you can read out just one of the qubits and you can not touch the state of any of the other ones, then you can start to use that error correction techniques to repair any kind of potential qubit phase error or bit flip.
You know, when you mentioned silicon, I just realized that last week, 2 weeks ago, last week, we installed in MIT.nano the new focused ion beam SEM system. And one of the sources is indeed silicon that is capable of producing 8 nanometer accuracy in positioning. Typically used for milling, but I imagine you might be able to use it for implantation just the same.
Yeah, we were just talking about that on the Slack, like right after the announcement came out. Super excited. If we can get down to a single ion level, that would be amazing.
Well, it's worth a try. There's professional technical staff from Wraith that will be with us for the duration of the next couple of years. So yeah, we're hoping a whole bunch of new discoveries might be coming out of that. Let me conclude by asking one more question that came on the chat, which is, could you please comment on the performance of the current Boston quantum network, the speed of operation, losses, and such?
Yeah, so I took a little bit of leeway here, calling it a Boston quantum network. So actually, the main part of this work is building the little node for it. And as you can see all the way to the end here, let me also sit on this slide. So this actually hasn't been used yet in the quantum network. A couple caveats. The nitrogen vacancy, which is the emitter that I've been talking about for most of this, has some really, really nice qualities, especially when it comes to the quantum coherence of the electron spin, which is where we store the quantum information. Unfortunately, the optical properties of it struggle quite a bit. And as you can see from, you can see my mouse here, this CDF on the left here, the things that would end up in our devices are in this orange plot, which means that the line width is basically unusable for quantum devices because it's just too broad, and we'll get no overlap between 2 different NV centers because of that broad line. Now, to fix that, it is possible. The use of cavities would help drastically. In these early demonstrations, these actually aren't cavities yet. These are just nanowires. So if you remember, the cavity is basically a nanowire with holes. This just doesn't have the hole yet. And so we don't get any benefits from putting it in a cavity yet at the device layer. Now, the other thing I want to mention is the thing that we actually put in these is not a nitrogen vacancy. Similar to this, this was using a silicon vacancy. We've also experimented with germanium vacancies. And I think we're still going down the periodic table there. And those have fantastic optical qualities in that when we implant them, even our implanted centers look very nice. And they don't suffer as much as a nitrogen vacancy does due to some symmetry arguments of what the defect actually looks like. But their electron spin is quite bad. Without getting into too much detail, you would need to either be able to do a lot more engineering to prevent phonons from interacting with these other centers, or you have to take it down to much, much colder temperatures. For the NV, you're good at 4 Kelvin, so you can just use a typical closed cycle cryostat for that. However, if you want to get silicon vacancy quantum performance from like a quantum memory perspective, you need to go down to dilution refrigerator temperatures, which is something we're actively doing. So, well, not me anymore, but the rest of the lab and the collaborators are working towards using a silicon vacancy system in dilution refrigerators. But as you can imagine, if you're not familiar with a dilution refrigerator, the amount of engineering just to make that kind of experiment work is a whole nother ballgame. And just the last piece of the puzzle is all of these emitters emit in the visible. And so that's not great for optical fibers over long distance. There's a reason telecom is not in the visible and in the infrared. And the loss in the visible over the distance, even just to Harvard, would be insane to send a visible photon that far. I mean, it wouldn't even be worth talking about the rates because the rates would be so tiny. So another huge component of this that we're working on along with Lincoln Labs and Harvard is being able to take that visible photon and through frequency mixing, basically, turn it into a photon, an infrared or a telecom photon that would be able to actually make the journey across one of those optical links. And so the early results of that are looking promising, but until the fidelity of that operation is more well known, it's hard to put a prediction on what kind of rates we might get at the end of the day. I know that was a disappointing answer, but I hope it answered your question.
It was a great answer. Indeed, technology as brand new as this does take time to be developed, and you're showing us pathways towards that. So thank you very, very much for that. Thank you for a great talk, Michael. And I would like to make sure that those of you who are still attending are alerted to the next talk coming up this coming Thursday at 11 o'clock. Integrating object form and electronic function in rapid prototyping and personal fabrication. This will be delivered by Junyi Zhu. This particular upcoming talk will be actually the last of the Nano Explorations for the summer. We'll take a break in August, so make sure you don't miss it. Thank you very much, and I'm hopefully going to see all of you on this coming Thursday at 11. Take care.
Thanks, Vladimir.
Thank you.